To prove the chain rule, when we use the limit definition of the derivative, we get a numerator that isn't easily simplified due to the g of x plus h and f of g of x terms. To make things simpler, let's return to the composite function f of g of x and rewrite it as f of u, where u equals g of x. Also, suppose that f is differentiable at u equals g of x and g is differentiable at x. Let's deal with g of x plus h first. Since g prime of x exists, using the limit definition of the derivative, we obtain this. Let's define a new function n of h, which will help us simplify the g of x plus h part of the numerator of star. The function n of h will need two cases for h not equal to 0 and h equals 0. Note that this, and so n of h is continuous at h equals 0. For h not equal to 0, we can express g of x plus h from n of h. This also holds for h equals 0. By the same logic, but with different names for variables and functions, we can define a new function m of k, which will help us simplify the f of u part of star. We also need two cases for k not equal to 0 and k equals 0. By analogous steps, we'll find the following. 1. M of k is continuous at k equals 0 since this. For k not equal to 0, we can express f of u plus k from m of k. This also holds for k equals 0. Now, with the expressions here, we can simplify f of g of x plus h minus f of g of x, which is the numerator of the difference quotient of star. First, consider the left term of the numerator. Above, we let k equal this. Combining this with the right term of the numerator, the first term cancels out. Now, combining this further with the denominator of star, the h cancels out. All the prior work will be helpful since, when h approaches 0, not only does n of h approach 0, but also m of k approaches 0, since k equals this. Finally, we can compute the derivative.